In today's lesson, we will be focusing on what we call binomials. All right, and your objectives today are that students will be able to determine the different powers of binomials, and that students will be able to utilize Pascal's triangle and the binomial theorem to expand binomials and to solve problems. For our activator, we took a look at that pyramid, the different patterns, and we asked you to fill in the missing numbers. Well, let's just take a quick look at that. If we notice, we started with a 1. In the second line, we had 2 1s. Then as we went below, we continued to add a 1 going outward. It always starts with 1 going outward, okay, in both directions. But then, if we were to say 1 plus 1, that would give us a number below. 1 plus 2 gave us a 3. 2 plus 1 would give us 3. 1 plus 3 would be 4. A 1 would continue down here. The missing spot here would be 6 and 4 would give me 10. We'd have a 1. So here we would have 1, 7, 21, 35, 35, 21, 7, and 1. Hopefully you were able to see that pattern and you were able to see that the numbers below just corresponded to the sum of the two numbers above them. So in our instructional focus today, we're going to be looking at binomial powers and coefficients. We'll take a look at Pascal's triangle. That's what we were actually looking at in our activator. We're going to look at something called the binomial theorem, and we're going to look at some basic factorial identities. So let's start out by taking a look at binomial powers and coefficients. So first off, many mathematical discoveries have begun with the study of patterns. All right. So in this section, in this lesson, we're going to introduce an important polynomial theorem called the binomial theorem. All right, and the way in which we kind of set the stage for that is by observing some patterns. All right, and we're going to start by looking at how we would expand different binomial factors. For example, a plus b to the 0 is going to equal 1. A plus b to the first is just, a plus b, or 1 a to the first b to the 0 plus 1 a to the 0 b to the first. All right, it's just another way of writing a plus b. When we take a plus b squared, and you guys remember a plus b squared is just a plus b times a plus b, right? We do FOIL, you get, a squared plus 2ab plus b squared, right? This is a squared plus 2ab plus b squared. We did a lot of this with algebra 2, dealing with binomials. Well, we could write that as 1a squared b to the 0, because b to the 0 is just 1, 2a to the first b to the first, plus 1 a to the 0 b squared. And we're writing it out that way because the pattern in the exponents becomes something that we really want to look at. We're going to see patterns in the exponents, and we're going to see patterns in the coefficients in front of our different terms. When we get to a plus b to the third, we get 1a to the third b to the 0, 3a squared b to the first, 3a to the first b squared, 1a to the 0 b to the third. And if we start noticing or looking closely, we might actually notice some patterns right off the bat with the different coefficients. All right, but we're going to get into that in a little more detail as well. But we might notice. All right, and let's actually look at that. So I'm just going to highlight a couple numbers on here. These are going to be the coefficients in front of the terms. We have 1, 1, 1, 1, 2, 1. 1, 3, 3, 1, right? If you start looking at just these coefficients, you might notice that they're the exact same as the numbers in Pascal's triangle, or in that triangle that we saw before. If we start looking at the exponents, let's go back to that. Sorry about that. Okay, let's go back to that. If we start looking at the exponents, right? A to the first, a squared, a to the third, a to the fourth, a to the fifth. We might find a to the sixth on the next one. We might see that that exponent is increasing by 1 every time. The exponent for b stays the same, 0 every time. So what are some other patterns that you might see? Do you think you could determine what the expansion of a plus b to the sixth will look like? Take a couple minutes, look at those patterns, and see if you can come up with an idea as to what it will look like, a plus b to the sixth. All right? All right. Hopefully you had a chance to spend a little bit of time and look at that. So let's take a look at what's going to happen in that next term, all right, in that a plus b to the sixth. When we get to there, we're going to say that the powers of a, all right, are going to decrease from 6 to 0 by 1s. Notice, 1, 0, 2, 1, 0. It's just going down by 1 each time. 3, 2, 1, 0. All right, for the powers of b, it starts at 0 and is going up. The powers of b are going to increase from 0 to 6 by 1s. The coefficients, all right, the first two coefficients are going to be 1 and 6. The last two will be 6 and 1. Notice it's just going to be the sum. We're going to have a 15, a 20, a 15, a 6, etc. So if we were to write out the entire thing, we would say it's going to be 1, a to the 6th, b to the 0, plus, the next one's going to be 6, a to the 5th, b to the 1st, plus 15, a to the 4th, b squared, etc., etc., etc. All right, and it's not 15 to that. It's 15, a to the 4th, b squared, etc., all the way down to the end. And note, we're adding the coefficients as we go down, and we're just adding one more to the exponents, and we count up by 1 or down by 1, depending on a or b. So an interesting thing that we find is that the binomial coefficients that appear in that expansion are always the values of n choose r for r equals 0, 1, 2, 3, all the way to n. All right. One way in which we look at this, the classical notation for NCR in context of binomial coefficients is just we do this parentheses n over, and we don't put a line, just n r, like this. That just means n choose r. It's the same thing that we learned about in the previous lesson for combinations, but that's what it means. It's just another way to visually represent that. So how could we use n choose r to expand a binomial? All right, so that's what we want to take a look at next. So if we want to go ahead and use n choose r to expand the binomial, all right, we're going to enter 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, 5 choose 5. All right, when we do that entire list, all right, of 0 through 5, and we can actually do this all at once, I believe. So let's pull out our calculator and make sure that we can do it just like that. So in my calculator, I'm going to go ahead, I'm going to do 5, I'm going to go into math probability, I'm going to do NCR, but now I want to do that entire list, all right? And so in order to do the list, we need to use this same bracket that we see here, all right? So we're going to find that little bracket. And that button for the list is just, it's hard to see here in my picture, but it's just if you hit second in the left parenthesis, it gives you the button for list, and then you just do 0, comma, 1, comma, 2, comma, 3, comma, 4, comma, 5, and then we do the closing parenthesis, the second closing parenthesis. It gives you that closing bracket, and you hit enter, and it gives me the full set, 1, 5, 10, 10, 5, 1. All right, and that tells me all of the coefficients that we're going to be using. So that's where the 1, 5, 10, 10, 5, and 1 come from. Then we need to use the exponents. So it's going to be a to the 5th, b to the 0, but b to the 0 is just 1, so we don't put it. A to the 4th, b to the 1st, a to the 3rd, b squared, a squared, b to the 3rd, a, b to the 4th, and then just b to the 5th. So the exponents for a go up by 1 each time, the exponents for b, or for a go down by 1 each time, and the exponents for b go up by 1 each time. And that gives us the entire expansion. So if we wanted to do, a plus b to the 6th, it would just be 6 choose 0 to 6 to get the coefficients, and then we do the exponents 6, 5, 4, 3, 2, 1 for a, and then 0, 1, 2, 3, 4, 5, 6 for b. So this brings us to Pascal's triangle, which is this triangle pyramid. We call it that in honor of Blaise Pascal, who used it in his work, but he didn't discover it. It appeared much, much before that in an old Chinese text, and then it most likely came even before that. But this triangle is the one that we saw in the activator. We know that the next rows, we're just going to take the sum of the values, so 1, 6, 15, 20, 15, 6, 1. And now we can use that to obtain x plus y to the 6th. So, all right, so the first one's just 1. So 1x squared, or just x squared, plus 6, and why did I say x squared? It's not x squared, it's just x to the 6th. So it's x to the 6th, 1x to the 6th, plus 6x to the 5th y, plus 15x to the 4th, and it's not x to a power, 15x to the 4th y squared, plus 20 x to the 3rd, and I keep messing up when I write this, but x to the 3rd y to the 3rd, plus 15x squared y to the 4th, plus 6x y to the 5th, plus y to the 6th. All right, and so we're able to use Pascal's triangle to get the coefficients, and then we just start with the 6 for x, 0 for y, and then we just raise the exponent on y by 1 and decrease the exponent for x by 1 for each term as we go through. When we look at the example in the text, we see that, how we use Pascal's triangle to get the next row, and how it just plays out to get exactly what we showed for the binomial expansion. In mathematics, many times we can write a formula based on itself. All right, and this is what we call recursion. So there also exists a recursion formula for Pascal's triangle, where if we say n choose r is the same as n minus 1 choose r minus 1 plus n minus 1 choose r. Or we could write it as seen here, which is the exact same. All right, this is just another way to determine n choose r. It just shows just another breakdown for it. All right, and this is a recursion formula for n choose r, and it can be used with Pascal's triangle, and we'll see how it might be applied. So if we wanted to find the coefficient for example, x to the 10th in the expansion of x plus 2 to the 15th. Now this is a pretty complex type of problem, all right, because we're going to take x plus 2 to the 15th, and there's going to be a term that has x to the 10th power. And we want to know what is the coefficient in front of that x to the 10th term. Now you might say, oh, well, that's pretty easy if we just go down to the 15th row of Pascal's triangle and we just kind of put them all out there. Whichever one has x to the 10th, we'll get the coefficient from there. But that doesn't quite work out because of this number 2, because that's not a y, right? If we had the expansion of x plus y to the 15th, that would work out fine. But if we think about the x to the 10th term, we're going to have x to the 10th and then 2 to the 5th. So it's going to be whatever that coefficient would be times 2 to the 5th. All right. So the way in which we can think about doing this, all right, is the only term that we need to deal with is 15 choose 10, right? 15 choose 10 is that point, x to the 10th, 2 to the 5th. That's exactly what we just said. So to get 15 choose 10, it's 15 factorial over 10 factorial, 5 factorial, times 2 to the 5th. All right, that's just what I was saying on the previous slide, is that we wanted to get that value, whatever that coefficient is, which is, 15 choose 10, and then we needed to multiply it by 2 to the 5th. When we do that, you get 3003 times 32, which is 96,096 for the coefficient in front of that term. It would be very difficult to come up with that without using combinations, without using these shortcuts that we've learned about that are helping us to expand these binomials, because the numbers get so large so quickly. So all of this leads us to the binomial theorem, which states that for any positive integer n, the binomial a plus b to the n can be expanded to n choose 0 times a to the n, plus n choose 1 times a to the n minus 1b, plus n choose r, a to the n minus r b to the r, all the way down to n choose n b to the n. All right. And this is essentially a pattern. So if b were 5, it would be a to the 5th, a to the 4th, b to the 1st, a to the 3rd, etc. And this works where n over r, right, this n choose r is equal to n factorial over r factorial times n minus r factorial, which is what we learned about in previous lessons. So if we wanted to expand a binomial using the binomial theorem, and we're looking at 2x minus y squared to the 4th, how would we go about doing this? Well, we're going to have to break this down into 4 pieces, right? Actually, 5 pieces, because the first one is going to be 4 choose 0 times a, which in this case is 2x, to the n, which is 4. All right, plus 4 choose 1 times a, which is 2x, to the third, times b, which is negative y squared, negative y squared to the first, plus 4 choose 2 times 2x, quantity squared, times negative y squared squared, and so on, all the way until we've used all of the terms, all right? And we're going to go ahead and just take a look at the full solution here, which would expand to be a to the fourth plus 4a cubed to the b. So this is just the simple expansion if it was a plus b. And then everywhere we have a, we're going to plug in 2x. Everywhere where we have b, we're going to plug in negative y. And then we'll simplify. So that kind of breaks down to 2x to the fourth plus 4 times 2x to the third negative y squared, 6 times 2x squared minus y squared squared, etc., etc. Once you go through this and simplify, we end up with this right here, 16x to the fourth minus 32x cubed y squared plus 24x squared y to the fourth minus 8x y to the sixth plus y to the eighth. And you might wonder, well, why is this y to the eighth? I thought we were only going up to the fourth power. Well, because the original b, right, that value had y squared. So negative y squared to the fourth power gives me positive y to the eighth. So we can expand anything in a binomial. So the thought is, break it down as just a plus b to the n, whatever that n is, and then plug in the values and then simplify. So in this lesson, we learned about powers of binomials and how there exists observable patterns that are predictable. We use this understanding to better understand Pascal's triangle and how to apply that understanding to the binomial theorem to expand polynomials. We also used our background knowledge in determining combinations to help assist us in that as well. So you should be able to express powers of binomials, use combinatorics and Pascal's triangle for that matter to expand binomials, and you should be able to utilize the binomial theorem to more efficiently expand binomials.